Hey, this is Dr. Della Corte back with Physics 313R. Today, lecture 7, a review on classical gates, logic, and circuits in our Introduction for Quantum Computation. So, a reminder for everyone, we're basing these lectures off the book Quantum Computing for Everyone by Chris Bernard. Highly recommend that you read the chapters associated with the lectures in there. We have seen multiple times now what happens when you measure a spin or a qubit. You actually force them into a definite state. If you change the orientation of your measurement, you change the outcomes. Quite surprising. We also are now more familiar with our linear algebra. We are able to figure out if a set of cats forms an orthonormal basis, and we can express vectors in that orthonormal basis, and we can also find the length of such vectors. Wonderful. We found ways to represent qubits, maybe as spins of electrons or as polarization of photons. And we saw what happens when we have two spins that are getting entangled with each other and that they have something that looks like a spooky communication with each other. However, we showed last time that we should rather consider entanglement as a global property that exists between two qubits. And that came out of the Bell's test, which showed that somewhat convincingly that when you have two clocks and they get entangled, they're really no longer separate entities, but they become something that transcends that. Okay, wonderful. Now we're going to go into the basics of logic. And there's not a lot of quantum computing here, so hopefully this lecture won't be super long, but it will be a good refresher before we introduce quantum gates that lay the foundation for quantum algorithms next. So truth tables look like this. You have a table that has statements in it. We call a statement P, and such a statement can be, for example, it is raining outside, which is false right now here. But maybe where you are at, it's true. So it's a statement that has a binary answer. It's either a true statement or a false statement. If you have a true or false statement, then you can negate that statement. So, is it raining outside right now? No, it's not. Is it not raining outside? Yeah, it is not raining outside. And with human language, it can get very quickly very clunky when you want to put nots into statements. But if you just say P is my statement as a general placeholder, then to say not P is not very clunky. And all that not P does is says everything that was true is now false, everything that was false, it's now true. There can also be multiple statements. You might say, I am in America, statement number one. And statement number two is, and it is raining here. So yeah, you might be in America, that can be true or false, and it might be raining or not raining, true or false. So with two different statements, you can have four different states. And now you can perform logical operations on both of these statements. You can, for example, combine them with an and say, I am in America and it is raining. If both of those are true, then, well, you're in America and it's raining. This whole statement is true. But if you're in America and it's not raining, then I'm in America and it's raining is false because one of the two operands, whatever you want to call them, one of the two statements is false. So the end statement effectively checks, are both of these things true? Yep, then this is true. Otherwise, they're all false. You can also put in an or statement. And this, I'm in America or it's raining. If you live in Great Britain, your chance of rain is pretty high. Your chance of being in America is very low. So you get or the or statement as soon as one of the operands is true, the or connection is true. And then there's this other one, the so-called exclusive or. I kind of warned you before, there's going to be a sign in this class that looks similar to our tensor product. This exclusive or is this guy here. it is a circle with a plus, not with an X, a plus in it. And that one is true if and only if one of the operands is true. So if both of them, if you're in America and it's raining, then the exclusive OR is false because this, yeah, that's just what the exclusive OR does. It says if two things are true, the exclusive OR between them says, oh, then it's false. Sometimes it's also called the addition modulo 2. So if both of these truths would be represented as a 1 and you add them together, 1 plus 1 is a 2, and you calculate the remainder after division by 2, the remainder would be 0. It's a false. So that's where this plus sign comes from, because it's when you actually want to do the math, it's like the idea of adding these two values together and then dividing by 2 and checking if there's a rest. If 1 and 0 is added together, it's 1. Divide that by 2, the rest is still 1, so the rest is a true. Okay, cool. So those are the 4 operands that we're going to deal with. You can combine these and you can build really large, complicated truth tables. I had some fun with that when I reviewed that a few months ago. So you could, for example, form a statement like that. And that's something I would recommend you to do in your study journal. So how would you go about that? You would take two statements, P and Q, and then you first calculate what is the not P. Then you calculate what is the not Q. And then you would calculate what is the not P and not Q. So that is looking here. FF, yeah, that's true. FF, yeah, it's false. FT is false. TF is false. TT is true, right? The end statement. And then you have to negate that whole thing and make it not. So that's true, 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 and false. Do you notice something when you look carefully? This outcome here is the same as this outcome. So there's an equivalence between this complicated statement and P or Q. So we're actually able to represent an OR through multiple negations and an AND, which is a neat result. Oh, I guess I have it on the slide. So logically, these two are equivalent. Why is that not letting me grab my thing? And similar to how this OR statement can be expressed with nots and ands, you can also, and this is a little bit harder to convince yourself of, but you just have to extend this list of truth tables. You can convince yourself that this more complicated connection of nots and ands will be the same as an exclusive OR, which means that you're able to represent all of these logical combinations through just negations and ands. And that's pretty cool. I'm going to talk about that a little bit later in the context of functional completeness. Functional completeness means you're able to reach every possible outcome in your outcome space with a small subset of operations, functions. So if we have 3 possible inputs, so 3 statements, P, Q, and R, then we all of a sudden have 8 possible combinations of which statement is true and which ones is false. And if you have a function f that takes the statements P, Q, and R as inputs that are either false or true, no matter what that function is, you can always build it, assemble it, just with a smart combination of nots and ands, because nots and ands are are functionally complete. How would you do it? Well, let's say you randomly just throw down some letters here, FFT, FFT, FT. Then you ask yourself, how can I build a function that gives me this response? Well, if you want to get a true right here, this guy, then you have to make sure that the statement says, well, I want to get a true only if my P statement is true, and my Q statement is not true, and my R statement is true. So P and not Q and R will give you this T here. So I'm able to build these rules for each of these rows to give me exactly that outcome, which is quite neat. So here we have another example. Not P and Q and not R is going to give me a true here. And another one. Great. So if you start writing these out for all of them, then you can build your complete function f by combining these individual statements with or. And we have seen before that an or can be replaced with a very complicated and not combination. So you can rewrite all of these ors again into and statements, and then you get this really beautiful thing down here, right? You might not agree that that's beautiful, but logically speaking, it's kind of nice that any truth table that you build, you will be able to find a function that just uses and nots and these free statements, however many inputs you have, to define that function. And once you have it, you can perform logical algebra on it to simplify it. Like many knots cancel with each other, and you can simplify, which I think we're doing here. Okay, great. So this set of operations not and and is a functionally complete set. So we can represent any functions in a truth table just with nots and ands. Wonderful. Now there's a different symbol, the NAND. That is the N and the not and and combination. So the not and. So that is represented with this arrow up. And it's equal to saying, take the two statements P and Q, do the and on them, and then do the not. And the neat thing about this statement is it's also functionally complete. Okay, here's the truth table for and not, for not and and. Great. Okay. So what this table here shows is that if I have a statement P and I and the statement with itself, which doesn't sound too smart, but yeah, we do it just P and P. If P is true, then P and P is true. If P is false, P and P is false. But then we throw a not in there, then a P and P turns into a false, and not P and P turns into a true. So what you see is that these values here are the inverse of the values over here. And so if we use 2 times the same input, P and P, inside of this NAND operator, that gives us a negation. So that's how you can get the negation. And if we use the negation of the NAND between two operands P and Q, let's do the math here. So if we take the not P and Q and replace that with our NAND definition, then we get P and Q is the same as not P NAND Q. And this guy, we already know, is the same as not P. So what we have shown is that P and Q can be represented as the three triple NANDs, P NAND Q, NAND P NAND Q. Well, you might be completely lost at this point, which is completely fine. The one thing that you want to remember here is that with these NAND logical operations, we are able to express nots and ands. And since nots and ands are functionally complete, NAND that replaces both of them is also functionally complete. And finally, we want to make the switch from these Boolean statements that are true and false to actually Boolean values to 0 and 1s. And the way we have dealt with it in this class is we have called um, truth. So typically, a true value is a one, and a false value is a zero. And so truth tables typically list the truths at the top, and so the zeros are typically listed at the top, though, so they're kind of inverted. That's the only thing we're doing here. We're going from the true and false to the zeros and ones, as the rest of the book and the class will do. And so the only thing we have to remember is that there's this little switch going on, but we don't really need it as long as we know in our mind that what a zero represents is not the zero represents a false and the one represents a true. Okay, great. By the way, this little arrow up is sometimes called a Sheffer stroke. I haven't heard it anywhere else in my life before, but if you're someone that likes little facts, you might like that. Great, cool. Now let's talk about gates. We're very grateful to smart people that have done wonderful things, and some of them are very young when they did them. So this one particularly goes to C. Shannon, who did that as a graduate student in his master's at MIT. He had the idea that if we can take all of logic and represent it with these truth tables and basic operations, if we are able to build an electric circuit to capture the absence or presence of electricity and encode that as a zero or one, so zero is no signal and one is on or true electricity there, then we might be able to rig up a machine that allows us to do computations. And so for that, he has built a bunch of gates, and they have visual representations. The NOT gate is presented. So this arrow means it flows in from the left, and then the little circle means it got negated. The AND gate says it flows in from the left here, and then it comes together with this round head and becomes an output. And the OR gate is looks kind of like the AND gate, but it is a little bit more arrow-like and it has a round back. And then finally, the NAND gate is the combination of the AND gate with the NOT circle. Great. So if you have a logical statement like not P and not Q, you can rig up a circuit that's made up of these four elements that represents this. So here is, for example, a input P that goes through a NOT gate that gets you the NOT P. The input Q goes through a NOT gate, gets you the NOT Q. They're both combined in the AND gate to give you a NOT P and NOT Q, and then you negate that whole thing for the not P and not Q. All right. And similarly, you could do that also with the NAND gate. I think I'm doing it here for you, but yeah, just P and Q go in, you send them through a NAND gate. So the AND and the NOT. So that gets you then P and Q. And then you do something here that is called a fan out. You make the same input go twice into an AND gate. So you have this in, let me just mark this up. So this input here, come on, is going in here and here by fanning out. And then you have it come in once here and once here. They both go in, and then the final output is the NAND of those two operands. Okay. If you want to learn how to do operations and things with it, there's much stuff you can learn in further CS classes. For now, we are just okay accepting that there are these wonderful gates, and they do what these truth tables predicted they would do. All right, now we want to talk about a concept called reversible computation. That means given an output, are we able to infer what the input was? So for example, with the AND gate, if the output is 0001, are we able to say what the input was? Well, if the output was 1, we clearly know the inputs were 1 and 1. But since 3 times the output 0 comes from 3 different inputs, there's no way of making a reversible statement. So a simple AND gate is not reversible. Shannon went on to calculate wonderful things related to the entropy and the loss of energy and information. And so here's the idea: whenever something runs through an AND gate, you actually lose some information because you no longer know the connection between inputs and outputs. So that must be heating up the universe. And so the Shannon entropy that is related to that is oftentimes um, is a frequently discussed concept that you might have heard of before. All right. So what's a C not gate? A C not stands for controlled not gate, and it's like the AND gate. However, it also has an extra output. So when we represent that here, we say we have an X that goes in and a Y that goes in. They are both combined with this C naught or addition modulus 2 operand here. The X comes out though, and this whatever comes out of this calculation comes out. The key idea here is that instead of just having a single output, we are also outputting the input X again. And by doing that, we are now creating a one-to-one relationship between input and output combinations that allows us to reverse back from the output to what the inputs were. So if the output was 0, 0, the inputs were 0, 0. If the outputs were 1, 0, then inputs were 1, 1. So that's quite neat. A different gate that you can rig up is called the Toffoli gate. That one is operating on 3 inputs, and it gives you 3 outputs. So because there's a 3-to-3 relationship, you can again from each output go back to a specific input gate. And the way this works is the X is just passed on, the Y is passed on, and the Z is being denoted with the combination of X and Y. So the interesting part here, of course, is any of these gates could potentially be used in a circuit. And the question is, can we build any arbitrary circuit out of these gates? And it turns out that the Toffoli gate is functionally complete, which means that we can build any type of computer just of gates that look like this. In general, some good idea that we can take away from it is if we want to create reversible gates, we need to make sure that the number of inputs and the number of outputs are the same. If you do not have a function with 5 inputs, but you have 5 outputs, then you need to create additional dummy inputs. They're called ancilla bits. Or if you only have one output that you care about, you can still spit out here like the X and the Y that seem not to contain any information. So kind of garbage bits that you produce, but these garbage bits allow you to afterwards construct a truth table that is reversible. Okay, great. Then there is this other gate we want to quickly talk about, the Fredkin gate, which is also functionally complete. And Fredkin is a very, he passed away 2 years ago, but he was a very influential scientist and had some very strong ideas that are not widely shared, but he had some really cool, insightful, brilliant ideas as well. So what does the Fredkin gate do? Similar to the Toffoli gate, it has 3 inputs and 3 outputs, so it's reversible. And what it does is it uses the first input bit to decide if the output bits Y and Z should be switched. So if my input X is 0, then my Y and my Z won't be touched. But if my input X is 1, then my Y will become the X. So you can see if the Y was 0 and the Z was 1, then the Y becomes 1 and the Z becomes 0. So X is a switch that tells you if Y and Z should switch their value. So we call this the control bit. And it's represented like this. And similar to Toffoli, it's also a universal gate. And there are different ways of representing it. One of them is through this rather impressive combination of knots and ands. And you can convince yourself in your study journal that this is performing exactly the type of action that we wanted to have. And you have a function f, the x comes in, the x comes out. but the y will be subjected to this operation of knots and ands and ors, which will effectively flop its value, similar to how this one will flop its value if x is 1, but not otherwise. Cool. Yeah, so Fredkin, quite a cool guy. The reason why we introduced this gate is because you can build this gate out of mechanical components. And there was this idea of Feynman, we don't have to spend a lot of time on it, but effectively he said that you can build a Fredkin gate, this guy down here, out of billiard ball machines. And so the idea is that you can use a machine that looks like this. You have some walls and some exits, and you can shoot billiard balls in, either at position 1 or position 2. So if you shoot one in at position 1, you get one out at position 1. Since you didn't shoot one in at position 2, there's none coming out. If you shoot a ball in just at position 2, it's going to come out of position 2A, but nowhere else. If you now shoot two of them in, one at 1 and one at 2, they're going to clank into each other. And after they clank into each other right here, they change each other's trajectory. The first ball is going to clank into this wall. The second ball is clanking into this wall. By the time the first one is clanked into the wall and came down here and sits right there, the second ball will be sitting right here, and they clank against into each other. And the in ball still comes out of the out, but the out 1, but the in ball 2 comes out at the out 2. And so you are able to use that to build up this switch gate here. So the truth table for it is down now. Let me move my thing around. So if no ball comes in at 1, then no comes out at 1. But if one comes in at 1, it will come out at 2. If you have a ball just coming in at 2A, but not at 1, it comes out at 2A. If it comes in at 2B, at 2 and at 1, you have one come out at 1 and at 2B. And this switch gate is equivalent to what we have seen before with the X and Y operations here. And so we are able to construct this type of billiard ball machine and make it a small black box that is shown as this rectangular box here, and say if we have an X and a Y, which are the billiard balls come in, there are 3 outputs. The first output is just the X that comes out. The second one, here the 2A, is the not X and Y output, and the 2B output is the X and Y output. So you're getting a complicated logical calculation with this billiard ball machine where the X and Y are combined in these 3 different ways. And then you can also build the inverse of that. And instead of sending these balls out, you send those balls in from the right. And then you can work yourself through the logic of how they would bounce to come out at 1 and 2. And you would see that this is possible to build as well. And if you have these 2 components built out of these billiard ball machines, you can rig them up in this rather complicated picture that you may or may not want to analyze in detail. But this one, if you time the duration it takes for the balls correctly to go from one to the other, will rig up exactly the same outcomes here at the bottom that the Fredkin gate predicts. And so if you take this box, this combination of 4 of these billiard ball machines and build that into one compact black box unit, you can say this black box unit does the same thing as the Fredkin gate. And since the Fredkin gate is universal, this box is also universal. And we can compute anything we want by stitching a lot of these gates together. Absolutely nothing you want to do, right? It's a terrible idea, but it's a nice thought principle of doing calculations with just billiard balls. So anyway, that's it for today. Next time we're going to look into actual quantum gates, but hopefully this sets the stage for it well. See you then.